Hello students, today we are going to learn about electric potential and capacitance. In this, students will be able to understand the meaning of the electric potential of a point and the potential difference. And also can easily derive the expression for the electric potential due to a point and also the dipole. Let us see in detail, children. Electric potential. See, the electric potential which plays a similar role of the flow of charges from one point to another, we can say. And the positive charge which always moves from the point from the higher potential to the lower potential. See, a positive test charge, we can say that when it's left free in an electric field which moves in the direction of the electric field. See, from the behavior of the positive test charge, you may be tempted that to say it is maybe the electric field and the electric potential or maybe very close relation. See, from this lesson, you may understand that and you may learn to establish the relation between these physical quantities. Let us see in detail, children. Yes, now, electric potential. See, the electric potential, which means we can say the flow of charges from one body to another. Or we can say that the electrical potential at a point in an electric field, which is the amount of work which is done in moving a unit positive charge from infinite to particular point against the electrostatic force, right? So, the electric potential, we can say that the work done by charge. So, according to the statement or the definitions, we can say that the work done, which means W AB whole divided by Q naught. So, W by Q we can say. Here Q by 4 pi epsilon naught into 1 by RB minus RA, which we have taken from the work done, which means what? F dot D, right? That is force into the distance, we can say that. So, that we can take it from the Coulomb's law. So, if you want to know about this chapter thoroughly, you must know and you have to previous chapter again and again you have to see that. Then only the chapter is interlinked. Both the chapters are interlinked with each other. That derivation will come here also. So that W which is equal to work done, as we said, work done which means force into distance. So force which we can say that from the Coulombs, we can take it the electrostatic force. Because of that, we can take Coulomb's electrostatic force. So Q by 4 pi epsilon naught into 1 by RB minus 1 by RA. So that here we said W infinite into B. So infinite means from the infinity to 1 point. So that W infinite B whole divided by Q naught. So which is equal to Q by 4 pi epsilon into R. That term we can call it as V, which means what? Electric potential. So V electric potential which is equal to W by Q naught. So, the SI unit of the electric potential is volt and we can say that joule per coulomb or Newton meter per coulomb. Now, we can say that if suppose the electric potential at a point is 1 volt, which means 1 joule of work is done in moving 1 coulomb of charge from infinite to the particular point in the electric field. So, electric potential difference. See, potential difference between 2 points, which means we can say that as the work done in moving a unit positive charge from one point to another. See, as we said that the electric potential in general, the charge which is the work done moving a unit positive charge from infinite to the point. The differences between the 2 points means the charge, if suppose kept in one point, we are moving. Some work has to be done against moving the charge from one point to another, we can say the differences between the 2 points, the potential differences between 2 points, or you understand that, right? Now, WAB, which is equal to, we can say it minus integration A to B E dot DI, that is equal to QQ naught by 4 pi epsilon naught 1 by RB minus 1 by RA. This part we have explained there in detail by explaining in the time of electric potential in general. So, this is the same thing, but this is between the 2 points, that's it. So, WAB whole divided by Q naught, which is equal to Q by 4 pi epsilon naught into 1 by RB minus Q by 4 pi epsilon naught 1 by RA. That we can say VB minus VA. That means what? Electric potential in one point minus electric potential in another point. So that is the difference between the 2 points. We can easily identify and calculate it. Or we can say that dull V. So which is equal to what? W by Q naught. And the electric potential and the potential differences are actually the scalar quantities, and the potential at infinite is 0. Right. Now, the electric potential which is near an isolated positive charge means Q which is greater than 0 is positive, and the near the isolated negative charge means Q is less than 0 which is negative. Got it? Now, the electric potential due to a single point charge. See the diagram on the screen. We have taken a positive point charge Q which is placed at the origin. Okay. Now, actually we wish to calculate the electric potential at a point P, a distance R from it. Suppose we have take a test charge plus Q naught and it is placed at P at the distance X from the source charge, which means we can say that the Coulomb's, from the Coulomb's law, the electrostatic force acting on charge Q naught is F which is equal to 1 by 4 pi epsilon naught Q naught by R square, or we can take here the distance is X means X square. So here we must know about one thing, the force F which is equal to plus Q naught E, and this is radially outward and tends to accelerate the test charge. We can see the derivation in detail. So as we said, we have taken a positive point charge which is placed, and the test charge Q naught is placed at A, the distance from X. So as per the Coulomb's law, what we said? F which is equal to 1 by 4 pi epsilon naught Q naught by X square. Right. Now, to move the charge from one place to another, you have to, work has to be done there. Right. So work then to move the Q naught from P to Q through dx, some distance or some displacement we can say against Q naught E. Then small work has to be done. So small work done there. So dW which is equal to F dot dx. So the W work done which means what? F into X. So that here we can take dW. That means dW which is equal to F into dx, which is equal to F value what we have taken the force. So electrostatic force which is equal to Q naught E. This is from the E which is equal to F by Q naught. So that I am telling that both the chapters are interlinked with each other. The E electrostatic field, from that we have taken this value. So F dx which is equal to F which is equal to what? Q naught E into dx. So we are applying the value dW which is equal to Q naught E into dx cos 180. Cos 180 means minus 1. So that minus Q naught E into dx we have taken. So dW on the whole, what is the value? Minus Q naught whole divided by 4 pi epsilon naught into X square into dx. So we need here the value of E. So E which is equal to what? Q into 4 pi epsilon naught X square. So from that it came. The total work done to move the charge. So we have only know the small displacement. So that small work we have taken. On the whole, for the whole system we need means the total work done we have to calculate it. So the total work done to move Q naught from A to B, which means what will come? Integrate. The system has to be integrate. The whole integrate, when we done it, we will get for the whole system. So W which is equal to integration of infinite to B, dW which is equal to minus of integration infinite to R, Q naught by 4 pi epsilon naught X square into dx. So that Q naught 4 pi epsilon naught is a constant value, we can take it out. We need to integrate only for 1 by X square into dx. Okay, so 1 by X square of dx we can integrate it, means finally we simplified and got the answer is Q by 4 pi epsilon naught into R. So W by Q which is equal to what? V. So V which is equal to Q by 4 pi epsilon naught into R. Now let us see the electric potential due to a group of point charges. We have seen before previous slide the electric potential due to a single point charge. If suppose we kept a number of charges in a system, so what will be the electric potential due to the group of point charges? Just we have to add add the algebraic sum of the individual potential. So it will not affect the presence of other charge. The electric potential will not get affected because of the presence of the other charge, right? So that simply we can add the algebraic sum of their individual potential. We can say that the group of point charges. Okay. So what is the value for V actually? V which is equal to Q by 4 pi epsilon naught into R. So here Vp which is equal to V1 plus V2 plus V3 till n number of charges. So that Vn we can say. So V which is equal to what? Formula when we apply 1 by 4 pi epsilon naught into summation of I which is equal to 1 to n Qi by Ri. So we need for that whole system, so that Ri it will be come to that modulus of R vector minus Ri vector. So in terms of we have taken the position vectors. So by applying the position vector value, we will get V which is equal to 1 by 4 pi epsilon naught into summation of I which is equal to 1 to n Qi by modulus of R vector minus Ri vector. As we said, the electric potential at a point due to the charge is not affected by the presence of other charges. And also here you must know about the differences between the potential and the Coulomb's force. So the potential here V which is equal to what we said. The formula, see the formula 1 by 4 pi epsilon naught Q by R. So that the V which is inversely proportional to only R, distance between them. But the Coulomb's force F is directly proportional to, inversely proportional to 1 by R square, because F which is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, the square of the distance between them. So that is inversely proportional, the square of the distance. Got it? The differences between that both. And we can say that the potential is the scalar, whereas the force is a vector one. Right? So we can see now to derive the expression for the electric potential at a point charge along the axial line of the dipole. If suppose the charge which is kept on the axis, that means we can say the axial line charge, right? So it is the dipole, we kept the dipole. That means we can say the diagram, you may see the diagram on the screen. This consists of the 2 point charges, that is minus Q plus Q, which is separated at the distance of 2L. This we can call it as the electric dipole. This is only the electric dipole. So let P be the point on the axis of the dipole at distance x from its center. Now, we need to calculate the electric potential at point P due to the dipole. We just have to add both the charges value. So, V which is equal to, we can say V1 plus V2 or V plus Q value, V minus Q value. So, one by one value we can say now, right? So, Vp plus Q value which is equal to 1 by 4 pi epsilon naught into Q by that R value. That R value here we have taken x minus L. So, see the x value which is from the center to that point, you have to minus the value of L, the half distance you have to reduce it. So, we have taken Q by x minus L. So, Vp minus Q which is equal to what it will come? 1 by 4 pi epsilon naught minus Q whole divided by x plus L. Here we have to add the L value. Okay. So, here what we said for that electric potential due to a point, that at point due to the dipole V which is equal to Vp plus Q plus Vp minus Q. So, only just we have to add it. So, we will get Vp which is equal to Q by 4 pi epsilon naught into 1 by x minus L minus 1 by x plus L, only you can keep it inside. So, 1 by A minus 1 by B, the algebraic formula we can use it here, 1 by A minus 1 by B, in that same way it is there, right? 1 by x minus L minus 1 by x plus L. By simplifying that, we will get 2L by x square minus L square. So, finally what value we got? Vp which is equal to 1 by 4 pi epsilon naught Q into 2L whole divided by x square minus L square. So, Q into 2L which means we know that is momentum, that is P which is equal to dipole momentum. So, Q into 2L is dipole moment. So, Vp which is equal to 1 by 4 pi epsilon naught P by x square minus L square. Now, let us see the second application. If suppose the point charge which is on the equatorial line which we can say that near the particular point or the dipole, near the dipole, if we kept, suppose you can see the diagram on the screen. We can take a dipole. The dipole always what? It consists of the minus Q plus Q charges, and that is separated by the distance 2a. Now P, which is the point on the perpendicular bisector on the dipole at a distance r from it. So that we can say its center. From its center it is situated. Now we have to calculate the electric potential at point P due to the dipole. That is what we have to just to add it. V1 and V2, or we can say VQ minus Q plus Q, right? So what is the value for plus Q? So V plus Q, which is equal to 1 by 4 pi epsilon naught Q by BQ. You have to take along BQ value, that is for the plus Q. And here you have taken for minus Q, means you have to take it 1 by 4 pi epsilon naught minus Q whole divided by AQ. That AQ part you have to take it. So by added up that both, we will get Q by 4 pi epsilon naught 1 by BQ minus 1 by AQ. Here, see that the value of 1 by BQ, that is, we can say that Q by root of R square plus L square. So we can say for minus Q value also, that we can take minus Q by AQ, right? So minus Q by AQ value we can take it here. Also minus Q whole divided by root of R square plus A square. So plus and minus both will get cancelled out. So that we can say that VQ, which is equal to 0. So the net electrostatic potential at a point in the electric field due to an electric dipole at any point on the equatorial line means it will be get 0. So let us assess by some questions I'll ask that, right? See that Q1, that is question number 1, a positive charge Q which is located at a point. What is the work done if a unit positive charge is carried once round, discharged along the circle of the radius r about this point? We can say work done is 0. How? Because of the force on the unit positive charge is along the radius and the direction of motion is perpendicular to it. So we can say W, which is equal to what? F is cos 90, perpendicular to that. So cos 90 will come. So the work done obviously will be 0. So the second question, in a 10 volt battery, how much work is done when a positively charged particle having the charge 1.6 into 10 power minus 19 coulomb, which is moved from its negative terminal to the positive terminal? Now, the base formula is what? V, potential, which is equal to work done by Q naught, charge, right? Since V, which is equal to 10 volt, and they have given Q naught value is what? 1.6 into 10 power minus 19 coulomb. So that we have to know about the work done. So W, which is equal to 10 volt into 1.6 into 10 power minus 19 coulomb. We calculated that value will come as 1.6 into 10 power minus 18 joule. So far we have learned from this video about the electric potential and the potential difference, and we have learned the electric potential due to a single charge, right? And we have learned about the single charge and also the group of charges, and the electric potential due to an electric dipole.